Okay guys, so turn to page please 418, problem 8.27, and now we are going to solve one problem which related to the magnetization issue. So now we are given a very long cylindrical conductor which has a radius of A and has permeability of mu naught mu r, for example, and then now we are going to find the M, the magnetization vector, as well as the Jm or JBN in your book. It's a Jm, it refers to magnetization's volume current density. Alright, and assuming that the current uniformly distributed along the cross section here of the cable. So now since we have assume that this is a very long conductor, so we can simply use ACL to calculate the H. So now let's apply the ACL, the close integrations. H dot dl equal to the I enclosed. So we know that, guys, the current now, actually assuming that the current flowing in that directions where we place or position the conductor along the z-axis, so that's our total current flowing within the conductor. So I'm going to calculate the H field that exists within this cable or conductor. So again, as normal, we have to choose any point of interest within this region. So let's say this is my point of interest, and then we have to draw our Amperian loop that must pass through the point as well as must completely close, and then with certain radius of r. Okay, so from this equation we can have the H 2 pi r for the circumference of the loop, and then the I includes actually the I that contained within this loop only. So we can simply apply this method J ds and then we know that the J can be obtained by dividing total current over total area, which is I over pi a squared, and then J now actually flowing in positive z directions, our summations, and then dot ds must be same also in z directions, which is r dr dv. Okay guys, so if we proceed as usual, we can have this expressions 2 pi r is equal to the I r squared over a squared. Then let's simplify the expressions r1 and r2 over there, and you can have the H vector equal to the I r 2 pi a squared in v directions. Alright, so that's the H. Now we're going to find the magnetization vector as required by the question. So the M can be related to the H by this equation psi m H, whereby this psi m refers to the magnetic susceptibility, and as we discussed previously, we know that, guys, the 1 plus psi m is equal to the relative permeability. So but we can simply find the psi m from this equation. So to find the magnetization is equal to the mu r minus 1, and then with the H obtained earlier, this is our H, I r over 2 pi a squared in v directions. Also it has same unit with H vector. Okay guys, so that's the M that actually exists within the conductor, and now we are going to find the Jm, the magnetization's volume current density. So if you recall from our previous lecture, we know that the Jm can be obtained using curl of M. Okay guys, so if you turn to the page 85 in Sadiko book, you will see that there are 3 tables on curl operations for Cartesian, cylindrical, and also for spherical. So for this case, please refer to the table or equation 3.45, page 85. So let me write down for you the expressions of the curl for case of cylindrical. So here we're gonna have 1 over r d m z component over d phi minus d m phi component over dz. So the whole term here belongs to, r component, then plus the second one, d m in r component over dz minus d m z component over dr, and now this whole term, guys, is belong to the phi component. And then lastly, for the z component, actually we have here 1 over r. Now we have d, which is r and phi component over dr, right, minus d mr component over d phi, and the whole term here belongs to z component. Okay guys, so now let's look at what we have now from the expressions of m that we obtained earlier. Actually the m only exists or only contain phi component, which is only here, right? This is our m phi component. It doesn't have any in r or even in z, so by that we can simply ignore this term 0. Same here 0, same here 0, same here 0, and now we left 2 terms up here and down here. So however, for this up term, it differentiates over dz, right, over z, but however in this m phi term there is no z parameter, so by again this differentiation will lead to 0 output. Okay, now we only have this term, so let's focus for the left term, and please substitute all these m phi into these equations. So now we have 1 over r d over dr. Now we have here r, mu r minus 1 ir 2 pi a squared. So now we have r times r, we got r squared. So take out all the constant outside, we're gonna have, and make sure that we have here z, right? So here must be z component, make sure, don't forget. So now we're gonna have here mu r minus 1 I, take out all the constant. Now here 2 pi a squared. Now we're gonna have here d over dr, r squared, right, and of course in z component. So let's proceed from here. We're gonna have the gm. So differentiate the r, so we're gonna have 2r, which will cancel out with the 2r down here. So finally you're gonna have these expressions, mu r minus 1 I, and then over pi a squared, and of course in z directions, and of course it has unit of ampere per meter. because this is magnetization's volume current density. Okay guys,